Today, we will explore how TV broadcasting signals are transmitted and recovered, focusing on the essential role of Fourier transform. In this process, Fourier analysis helps manage and understand signal behavior in the frequency domain, enabling clear and reliable broadcasting. We will break down the key modulation techniques, analyze signals with Fourier transform, and show a practical example to highlight how it all comes together. In electronics and telecommunication, modulation is the process of altering a current signal, such as a sine wave, to encode information, typically by changing its amplitude, frequency, or phase. This allows data to be transmitted over various mediums like radio waves or cables, making it suitable for communication. We have two ways for modulation, the analog carrier and digital carrier. The most commonly used types of modulation in telecommunications are PSK, phase shift keying, which refers to a finite number of phases used. PSK, frequency shift keying, which means a finite number of frequency used. ICK, amplitude shift keying, which in this case is a finite number of amplitude used. In this presentation, I am going to talk about QAM, quadrature amplitude modulation. QAM stands for a quadrature amplitude modulation, and it's the most common modulation the modern radios use to encode information onto our RF wave. The RF waves have three main properties that we can control to encode information onto them: the amplitude, the frequency, and phase. Digital communication systems work with ones and zeros, which are easy to encode. With amplitude modulation, a simple on-off switch is enough to encode 1 and 0. With frequency modulation, signals with two different frequencies do the job. And with phase modulation, it's shifting the signal by 180 degrees. The QAM modulation is a combination of amplitude and phase modulation. Everybody just the components of a sine wave. I own a sine wave has got a certain amplitude. We call that A. And then basically just follows this shape here, using a sinusoid function. 2p times the frequency, which is the 1 over the period times time, plus some offset in phase if we want to shift this wave for back and forth. So, very simple. If we are going to modulate this waveform, the properties that typically can get modulated are the amplitude, the frequency, or the phase. That's amplitude, IM, FM, or PM type modulation, and just about all modulation types are really just functions of those three things or combination of those three things. Just focusing in on amplitude modulation, or essentially doing is taking the amplitude term and making it some function of time, maybe like a slowly varying sine wave, and using that you multiply against the sinusoid function. And that we do is basically modulate or change the amplitude of that sine wave in response to that baseband signal. So now normally the modulation envelope, if you will, the baseband signal is much slower than the carrier, so you really can't see that. Is that of two signals are 90 degrees apart in phase, they are said to be in quadrature. Very simple, just a quarter cycle. In fact, a cosine wave and a sine wave are quadrature waveforms. You will actually see both plotted here. The blue waveform is a sine wave, and then the red waveform is a cosine wave. We can see that they are separated by a quarter cycle of 90 degrees, so they are quadrature waveforms. Each one of them can obviously have his own amplitude, and essentially for quadrature waveforms, what we do is we basically say that the amplitude of the cosine wave, we call that I, or the in phase signal. So that's I times the cosine of 2 pi ft. And then the amplitude of the quadrature waveform of the sine waveform is Q. So that's kind of given by the definition here. So Q times the sine, so since there are 90 degrees out of the phase, are quadrature signals, so since all the argument here is going to be the same, there are identical waveforms that just shifted by 90 degrees. The 90 degrees, but the only thing we really need to know are the I and Q values, and if we start changing the I and Q values versus time will change essentially the resulting sum of these two waveforms. When I and Q vary identically, the amplitude of the sum varies. When I and Q vary differently, the phase amplitude of sum varies. Therefore, I and Q results in amplitude and phase modulation of the sum frequency modulation. In this slide, I am going to explain a little bit how works constellation diagram. The symbols can be mapped into so-called constellation diagram. The QPS key has 4 possible symbols with 2 information bits per symbol. The 16 QAM has 16 symbols with 4 information bits per symbol. 64 has 64 symbols, and so on. So considering the A0211 AC standard and 20 MHz per channel, we need at least 5 dB CNR or QPSK, 11 dBs SNR for 16 QAM, 18 dBs SNR for 60 QAM, and so on. Is an example of FFT for an encoded signal and modulated signal. So this is a representation of how a current signal works with respect to amplitude as a function of the information signal. That is the modulation signal. This is the message. So the modulated signal is in this example is a complex 16 QAM signal carrying more data. So in this graph, we have an encoded signal directly represents the real part of QAM symbols sampled at the same rate. Results is an spectrum that spans a broader frequency range, as no carrier modulation confines its bandwidth. The encoded signal has a higher bandwidth as it contains a wider range of frequency components that can contain rapid changes such as abrupt transitions between high and low amplitudes. And we have the 16 QAM modulated signal. In this example, I am combining in phase and quadrature QAM components modulated with a carrier frequency FC 2000 Hz. The resulting spectrum shows sidebands around the carrier frequency with a narrower overall bandwidth. In this image, you can see the resulting spectrum. In this graph, the high bandwidth is more evident. Both the encoded signal and the 16 quant modulated signal are modulated by the same carrier frequency. Each 16 quant symbol represents 4 bits, so the bit string will be simple at 4 times the quant symbol rate. For frequency domain FFT spectrum, the unmodulated signal has a narrow spectrum around 100 Hz, and the 16 quant modulated signal has a broader frequency spectrum with frequency components spread over a wider range. These examples show the advantage of using FFT since it allows to visualize the frequency components of both modulated and modulated signal and to analyze the bandwidth required by the modulated signal. Thank you so much.